We're going to spend some time talking about probability distributions because down the road, when we're looking at hypothesis tests and some other kinds of statistical analyses, we make certain assumptions about how the data is distributed. And so by making sure we have a thorough understanding of probability distributions, that'll put us into a good position. So first of all, notice that probability distributions are divided into two major categories. And notice that we've got the discrete and the continuous. So the main dividing factor here, the real distinguishing trait, is that it has to do with what the data looks like. So discrete data, as we said, are things that can be counted. So, and these are going to be integer values. So, whole numbers that include 0. So, if we're doing counts, say we're counting customers, the number of customers that queue up, or we're counting factories, the number of factories in a certain area, or the number of treasury bills that are outstanding, or in that. So anything that you count is going to be fall under this heading of a discrete probability distribution. And so on the other hand, we've got these continuous probability distributions that deal with quantities that are measured with some kind of instrument. So these are quantities like height and weight and volume. And so these can take on all real values. So that means they're not constrained to being integers. They can be partial numbers. So for example, we can talk about 6.52 cubic centimeters, but we can't talk about 6.52 customers. So that's where these probability distributions are distinguished. Okay, so let's talk a little bit more about what we mean by a probability distribution. So recall some notation when we talk about probability. It has to do with the values of something called a random variable. Random variable. And this is just some variable whose value is subject to certain randomness, certain chance. So anything whose value is not subject to chance is called deterministic. And if we know something for sure, if something is deterministic, then we don't really use probability for it. But these other cases where we have some kind of value that's subject to chance, these are called stochastic. So that is, they're subject to a certain uncertainty and certain randomness. So that's why it's called a random variable. So the number of customers who show up, or how much rain falls. These are things that we don't. They're subject to chance. Okay, so a little bit of a review of notation. So when we have remember that when we were talking about classical probability, we wrote down notation like this, where the probability of event A was, something. Okay, so or the probability of rolling 2 heads. So remember that a random variable has something called a sample space, which includes all possible outcomes. So for example, with our coin, we had a sample space of head and tail. Okay, and with our with our die, had a sample space of 1, 2, 3, 4, 5, and 6. Okay. Now, with a random variable, we are interested in the probabilities, assigning probabilities to each of these individual events. So in this case, we would say, okay, well, we know that the probability of the heads is, the head is 0.5 and the probability of tail is 0.5. And for this die, each one of these is 1 over 6. Okay, so when we talk about a probability distribution, all that is a mapping from each event to the probability of that event. So, for example, like this, and this can take on a number of different forms. A convenient one for a discrete random variable is to just tabulate it. So we generally use for a random variable this notation where we say, okay, the random variable is denoted by some uppercase letter, usually X. If they start with X, and then if X is already used, they go to Y. But so we have this random variable X. Okay, so we put that there. That's the sorry. So this is the random variable X, and we're interested in the probability that the random variable X takes on some particular value, which is small x. Okay, so if we call our random variable D here, then we can write this: the probability that the random variable D takes on the value of 1 is equal to 1/6. Okay, so this is just this notation here. Sometimes there will be a little subscript here like x sub I, but just be aware that the uppercase denotes the random variable, whereas the lowercase x is a symbol for a particular value of the random variable. Okay, so when we talk about a probability distribution, all we're doing is just laying out each of the possible values and then assigning the probability of it. So we would say, okay, this would be x, and this is the probability. So this would be lowercase x. And this is the probability that the uppercase random variable takes on the value of x. So in this case, I can't fit them all, but I'm going to write just 1, 2, ... 6. And so the probability that this random variable takes on a 1 in this scenario here is 1/6, 1/6, ... 1/6. So a table is a convenient way to describe a discrete probability distribution. Okay, so let's talk about the difference then between two kinds of distributions. So there are those that we can come up with the distribution just by knowing something about the actual data generating process. So for example, if we want to know the probability distribution of a fair coin, then we know, just because the coin has two sides and it's balanced, that we should have, over the long term, 50-50 distribution, 0.5 probability of each side. So that's what's called a theoretical distribution. Theoretical distribution is one that we can deduce it from the parameters of the actual process. Okay, and so likewise with a die, we know that there are 6 sides and we know that it's balanced. So theoretically, we have a distribution where each value is going to take on the same probability, which is 1/6. But we also have cases where we can't really come up with any kind of general rule for what the probability distribution was. So let's say, for example, I want to know the probability of a certain number of computer network interruptions in a single day. Okay, so is there any way to theoretically come up with what that would be? Well, you could say, well, theoretically there's 0, but there's not really any real guiding theory that will tell you for sure that that will be 0. So what we have to do is just kind of look at historical data and then see how it fell out. And so what we call this is an empirical distribution. And so this is where we just look at historical data and then just come up with a table where we indicate how often we observed that value. So empirical just means that it comes from observation. And so this just means that we've collected the data and over time we've come up with a distribution. Okay, so let's take a look at this exact empirical distribution and then see if we can come up with certain descriptors of the distribution that will help us make management decisions. So, okay, so we've got a probability distribution, an empirically derived probability distribution that tells us that maps the interruptions per day in the computer network and the probability that that has happened. So this wasn't derived theoretically, this is just historically how it's happened. So what this is saying is 35% of the time in the past there has been 0, and 5% of the time it's been 5. Now, the first thing that we might ask, when we see a distribution like this is, okay, so we know that this is, these are probabilities. And we might want to ask, okay, well, the two major properties that we talked about were whether the events are mutually exclusive and whether they are collectively exhaustive. Okay, so are these mutually exclusive? Well, of course, we can't have both 1 and 2 on the same day. Okay, that can't, those both can't be the total count for a single day. So we know that it's mutually exclusive. Okay, so check. What about collectively exhaustive? Well, how would we know that? Well, if we add all these up, we can see that, let's see, 35 and 25, 60, 80, 90, and 100. So this adds up to 1. So what this tells me is that these constitute all possible cases. So they are collectively exhaustive. So there's a couple of observations that we can make about this. But let's think about how, now that we have this is a probability distribution because it is a mapping. So we've got a random variable x, which indicates the number of disruptions, right? Number of disruptions. And this gives us a probability that that random variable takes on a certain value. So we know that the probability that x is going to be equal to 4 is equal to 0.05. Okay, so this is just a discrete distribution. So this is just a probability distribution of a discrete random variable. Okay, so really it's just a table. So the thing you might ask now is, okay, well, we've got this. How does this help us? How does this give us any kind of insight, or how does this help us plan? Well, we might be interested in figuring out, well, what should we plan for? Given this probability distribution, how do we plan? How do we staff? What can we expect? So this gets into the concept of expected value. Okay. So what is the expected value? Okay, it's a symbol of E, stands for expected. What is the expected value of X? Okay, so what is our expected number of computer disruptions? Well, let's take a look at a simpler example and then kind of work with that. So we had our, let's say we're defining our discrete random variable as die throws. And the sample space here consists of 1, 2, 3, 4, 5, and 6. Okay. So if we were to say, what's the expected value of this? So conceptually, what this means is if we were to just roll the die a million times, what is going to be our long-term average? What will be our average roll over time? And that will give us some idea of what we can expect. Okay, so let's think about this. So we can make a table that will map each of these to its probability, but we know we can just say, okay, well, we know that's 1/6, and that's 1/6, and they're all 1/6. So if we were going to take an average of this, then what is an average? Well, we just we add up all the values and divide by the number. Okay, so we got 6 possible values, and so let's add these up and divide by 6. So our average then, so say the average of this is going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6. Okay, and this turns out to be 3.5. Okay, which is incidentally, the median of that. And there are reasons for that. So, but the fact that this is an average and that we were able to do it gives us a little bit of an intuitive understanding of how to come up with an expected value of a probability distribution. So what we can expect over time is that we will average to 3.5. Okay, now let's do a little bit of algebra. One of the nice things why we were able to just divide by 6 is because all of these values had the same probability. So let's think about how we might accommodate cases where we don't have the same probabilities. So let's do this. Let's do some algebra here. Let's pull this 1/6 out. So this is the same as 1/6 times this sum. Okay, now let's go ahead and distribute that 1/6 because we can do that. So it's going to be 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. Okay, now let's go ahead and put symbols on what these pieces are. Okay, so what is this 1/6? Well, that 1/6 is just telling us the probability that the random variable takes on this value of 1. Okay, so, and that's true for all of these. So let's just go ahead and say, well, what are each of these terms describing? So that is the probability that X is taking on, and then rather than just put in 1 for 1, 1 for 2, 1 for 3, I'm just going to say the probability that the random variable takes on this particular value. Okay, so that's the 1/6. And then we're multiplying it by the value itself. So times X sub I. Okay, and then what are we doing here? We are adding them all up okay? And the so the fancy symbol for that is we're going to be adding, okay? So all we're doing is we're taking an average, and if we factor out this denominator here, we see what we're doing is we're actually multiplying each value times the probability of that value. And so what this means is that in order to get the expected value of this distribution, we are adding up the probabilities for each value and then we're multiplying each value times its probability, and then we're adding them all up. Okay? And it turns out this is the formula for an expected value. Okay? So this shouldn't throw you now because this is what we just figured out. So for a discrete random variable, the expected value, also called the mean, we're going to use the Greek symbol mu for that. It's the same in this case as the expected value. Notice the uppercase X here. So it's the random variable. So it's telling us, okay, take each of those individual values and then multiply it times their probability. The probability that that variable takes on that particular value. Okay, and then add them all up. Okay. So this formula is just a shortcut for what we did over here in finding the average. So in addition to wanting to be able to plan around an average, we might also want to have some concept of how the values are dispersed. So, in addition to knowing, how many interruptions we have, we might want to take a look at the variance, because that will tell us how accurate that expected value really is. If there's a very high variance, then the mean is not going to tell us very much in terms of planning. Okay, and so the formula for the variance, and I'm going to go ahead and execute these in Excel to show you how it works. So we've got the mean up here, the expected value, and down here we've got the variance. Okay, and so notice that this piece is the same, so it's the probability. So we're still using the probability of each of the values. But this time, instead of multiplying it by the actual value, we're multiplying it by the squared distance of each value from this mean value. And then we add them all up. And this is going to give us the variance of x. Okay? And if we take the square root of all this, if we take the square root of the variance of x, then we just have the standard deviation. Okay, so sometimes just seeing these formulas here on the page can be kind of daunting. So let's go ahead and figure out both the expected value and the variance of this computer interruption problem. So I've copied down the table, okay, of the empirical distribution right here, and I've also written down the formulas for your reference and mine for the expected value and the variance right here. So okay, let's go ahead and do the expected value first. Okay. All right, so over here in Excel, I've copied down the table. So this is the interruptions, the number of interruptions 0 through 5, and this is the probability for each. So let's go ahead and find we're going to find the expected value of x. We're going to find the variance of x, and then we'll find the standard deviation of x. Okay, and we'll do it by constructing from these expressions over here. Okay, so the first thing we need to do is we've got the probabilities, and that's what this is, and we've got the x's, which is what this is. So what we need to do is take the product of these. So, and I'll call this x times p of x. Okay, so it's just going to be equal to this times this. Okay, and that's 0 because that's 0 disruptions, 0 interruptions. So I'll just copy that down. Okay, so that's the product. And then all we need to do now is add them all up. Okay, so I'm going to just put this right here and set this equal to the sum of all of these products. Okay, and so what this tells us is that the expected number of computer network interruptions is 1.4. Okay, and does this make sense given the historical data? Well, let's take a look. So 35% of the time we've had 0, 25% of the time we had 1. So we see that it looks like, over half the time we only had 0 or 1. But we still have kind of a long tail here going all the way up to 5. So it looks like 1.4 makes sense. So we should plan for 1.4. Now, how much variability is there in that? Well, let's go ahead and compute the variance taking each of these pieces. Okay, so once again, the probabilities here are just right here in this column. So we don't need to do anything with those. But now we need to take the distance from each individual x value from its mean. Okay, so remember the x's are the values that we're asking about, right? This is the actual number of interruptions. So we want to, I'll call this column x minus mean squared. Okay, that's what I'll just call that column. Okay, and we already calculated the mean. It's right down here. So I just need to do equals quantity. Okay, this is our x minus our average, which is down here. And then I'm going to push F4 because I want that to be an absolute reference. And then I'm going to square that. Okay, and then I'll just copy those down, copy and paste. And okay, so now I've got this part. And so I need to multiply it by this part. So we'll call this part just, we'll just call it product to save time. So this is going to be equal to, we'll keep them in order here, this times this probability here. Okay, and so we'll just copy that, paste it down. Okay, so now the only remaining piece is this summation here. So that's going to give us our final answer. So we'll just come down here to this cell and we'll say, okay, put down the sum of these. Okay. All right, so what is this telling us? This is telling us that the variance is 2, but of course the problem with the variance is that it's in squared units. So let's go ahead and take that square root to get it back down into something we can interpret. So square root of that. Okay, so and let's format these the same number of decimal places. Okay, so what this is telling us is that what we can expect is that we'll have 1.4 interruptions. Okay, so it's closer to 1 interruption than 2 interruptions. And the standard deviation is also around 1.4. Now, you want to be cautious about how you interpret the standard deviation here, because remember that the empirical rule tells us that 68% we can expect our value to fall, within 1 standard deviation of the mean 68% of the time. Well, the empirical rule only actually applies to normal distributions. This is not anywhere close to a normal distribution. In fact, I'll show you what it does look like. I will select this and then okay, make this chart. Now these labels aren't correct, so I'm going to right click and select the data that actually goes there. Okay. All right. So this is what it, well, okay, call this network interruptions. Okay, so we see that this is not normally distributed. It's not shaped like a bell curve. So our standard deviation is not going to tell us where 68% of the values are going to fall. So, but what this will tell us is it'll give us some idea of the dispersion. And so, we'll know that our guesses will tend, this is a fairly small standard deviation. So if this were, say, 6, then we would say that the data is so varied that it's going to be hard to plan around that. But as we see, we can go ahead and plan around 1.4 with confidence. Okay, so just as a quick review, so we talked about what exactly a probability distribution was, and we had the two major categories, the discrete and the continuous, and we looked at what we meant by a distribution. That is, it's just a mapping from observations in the event space or outcomes in the event space, sample space, to particular probabilities associated with those. And in the discrete case, we can do that with a table. And finally, we looked at, now that we have our probability distribution, how can we find its expected value, which is the same as the mean, and its variance. Okay, and we showed how to calculate those in Excel. And I will put these up on D2L, and I hope that helps.